Every positive two-digit number is greater than the product of its digits.
These students are developing their skills in mathematical argument and proof. In this lesson, they are thinking about the importance of structure in presenting mathematical proofs.
But what we're going to do is we're going to try to decide whether or not that is true, and if it is true, we're going to prove it. The aim was to try to help the students to be able to construct a very clear, rigorous proof of a result that they believe to be true. Could someone give me an example to determine whether it's true for that example?
99.
99. We explored a little bit until we tried to come up with a decision as to whether we thought it was always true or wasn't always true, and it certainly seemed to be happening all the time. But so far we haven't tried every single one, we've only tried 99. Could we try another one? 27. 27, 2 times 7 is? 14. This is looking good, isn't it? Are we happy to go through all 90 of them?
No.
No, we don't have time, so we're going to try to prove why. Right, you have got 2 minutes just to think how on earth you could go about proving that. For a couple of minutes they thought about, right, how could we actually show that? They found that quite difficult, and I think they find that quite difficult because it's not the sort of thing they do very much, although they have done a bit of proof before, but that 10a plus b as being an algebraic representation of the two-digit number AB, only one of the groups saw that. So after not too long, I kind of took them through that proof and showed them this is how we can produce a proof of this result that shows you that it always has to work. I'm going to give you...
The students are now given a proof to an algebraic statement, but as a series of cards. Each card has a different stage of the proof written on it. The students have to arrange the cards to make the proof.
I mean, this is going to be true, isn't it? Because obviously, like every 3 numbers is a multiple of 3 because you're adding.
Having the cards there, A, showed them the sort of thing that each step would look like, and B, showed them the little steps that you can take to go from the original statement to the final statement. I think it would have been very, very difficult to ask them, here's a result, prove it. You know, we found that quite difficult in the situation that we did, and the ones that we were looking at were probably slightly more complicated than that.
That's true. Yeah. But I mean, that's the
That's a stepping stone to be able to start structuring your own proofs. You could see the sorts of steps you take. You could see the sort of way that you can develop the way a proof's going to go before you actually go through the stages, so that when you actually come to proving something that you hope is true, you've kind of got modelled solutions, you've got an idea of what that process is going to look like. You recognise the rigour that each step has to take. You can't just make assumptions or ignore certain aspects of it. You've got to make sure each line follows from the line above and give them a much better idea of how to structure their own proofs.
And 18 is a multiple of 2 but not a multiple of 4.
When you do a card sort, it's a little bit different because it's the scaffolding's there, and they're not necessarily at a loss as to what the next step's going to be. They're talking about why this step is a better step than this step, so the tools they've got are slightly different. If there are in any 3 consecutive numbers, at least one will be a multiple of 3. Is that always true?
Yes.
Could you explain to me why that's always true? There were different sorts of interactions. Some of the interactions were talking about what the cards actually said, and some of the discussions I had with the students were, do you absolutely understand exactly what that card is saying? And then some of the discussions were about the order in which the cards were going to be put down and how one thing followed on from another. Very quickly they all kind of realised what the first couple of statements would look like and what the end was going to look like, and then it was a question of just trying to structure that, not just in terms of the step-by-step between each card, but also how that overall proof came together.
3 times 8.
3 times 8 is 24. Okay. One of the tricky things they found on some of the cards was understanding exactly how the individual card had come to the conclusion that it had. So just getting them to take a step back and make sure they were absolutely happy with how each one of those individual parts work. And for some of them who maybe hadn't quite got that far, just thinking about, right, what's the structure of this proof going to look like? Which ones of these statements look like they're getting towards the end product, and which ones look more like the start product, in order to have that argument running through from beginning to end.
Because you know that if one is a multiple of 4 and one is a multiple of 2, you multiply those 2 together, you get 8. And then it says here that you get all consecutive numbers are a multiple of 3. 8 times 3 is 24, which means that all of those would be the product of 24.
The students have to have some prior experience or concept of what's actually happening here, and probably start with some maybe very, very straightforward examples, and then just slowly build them up, trying to get them to understand that each step has to follow on from the step before it. The ideal is at the end that first of all they understand what the structure of a proof is, that they understand that it's not good enough just to have a statement that you think is true or that looks like it's true all the time. You've got to be able to explain why it will always work or prove that it will always work. To recognise that although the overall proof from statement to QED at the end can be quite complicated, the individual steps, if you can work out what they are and when to do them, really are quite straightforward.